for coming. Since we're going to work with Itai, who was supposed to be giving the talk, and then remember that he actually has to teach, and with Rann. So it's a talk about strategic communication. It's a huge literature basically trying to figure out how and to what extent can an informed party influence the behavior of others, but just through the provision of information. Selecting what information to share, how can you get people to do what you want? There are tons of applications. This is just some of the range of the applications. This paper that I'm presenting is not at all about any of these applications. It's a paper about a model. So I'm not going to go into the applications. But in any of these applications, if you're a researcher trying to understand what's going on in a particular setting, then so you're trying to understand, given the particular problem you're looking at, how much information you expect will be shared. And based on how much and what information will be shared, trying to predict or trying to understand what's going to happen in this particular interaction. And how much news will the media share, or how much, I don't know, information firms will disclose, or the central bank, how much of its published proceedings it will make public, or how transparent it will make them. And to try to figure out what's going on in these applications, the researchers typically will have a model of what's going on. And they'll use this model to try and predict and understand what's going on. And typically, we want these models to be robust. Right? Obviously, this is a model. These are simplifications of what's actually going on. So, there are idealizations of what's going on. And if the models are not robust, meaning that slight misspecifications of the model lead to dramatically different predictions, then the models aren't all that useful. Okay, so typically, we want these models to be robust. Now, in the context of strategic communication, there are different models of how communication takes place. Two of the models, one of them I'll mention, the other one is what this paper is about, are Bayesian persuasion and cheap talk. There are other models as well. There's, policy signaling, there's verifiable information. Yeah, but on the two extremes, we have Bayesian persuasion, we have cheap talk. I'll say a bit more about these in a bit. In both of these models, there's an informed party, which here is called the sender of the information. The informed party has some information about the state of the world. Then there's another party who has no information. This is the receiver, who receives the information from the sender, and the receiver takes an action, engages in some behavior. And this action influences the payoff of both the sender and the receiver. Now, typically, the sender and receiver will have different utility functions. Their incentives are not aligned. And so the sender might be selective in what information he sends to the receiver. If trying to get the receiver to take an action, it's more favorable to the sender rather than to the receiver. And these models, in a bunch of these applications, models are well understood. In particular, very often we're interested in what's called the sender optimal equilibrium, and the best information, the best manipulation the sender can do on the receiver, and what's optimal for the sender. And these equilibria are often well understood, as are the payoffs that are achievable by the sender, just by changing the information that the sender sees. And what we do in this paper is we look at these equilibrium payoffs of these sender optimal equilibrium payoffs, and we studied their robustness, a particular kind of robustness of these predictions. So we call this the informational robustness.
Does the receiver have an equal if no information is received?
Yeah. So the receiver has some action that will take, for whatever belief he ends up with, including his prior belief. Okay, so like I said, the main goal in these models of strategic communication is to try to figure out to what degree informational manipulation can be accomplished by the sender. And in order to try and understand this, a lot of these models make a very extreme assumption. The assumption in these models is that only the manipulating party, only the sender has any information, and the receiver has no information at all. There's a complete dichotomy of the information. And what we're asking in this paper is, what if this assumption is only approximately true? Maybe the sender has a lot more information than the receiver, but the receiver maybe has some marginal, little bit of information as well. Some other information source, maybe not as good as the sender, but something. What if the receiver is not completely ignorant? Okay, and this is where we're looking at the robustness question. If when you add a tiny bit of information to the receiver, you perturb the model a little bit, the predictions change dramatically, then the predictions aren't reliable anymore, they're not robust. Okay, so our question is, first of all, are the predictions robust? to maybe changing the informational environment a little bit. And if not, the predictions are not robust. Are there other predictions that are? Okay, what can we say? Okay, so this is what we study in this model. We formalize this question of the informational robustness in the following way, or slightly more formal. We're going to ask, okay, given a particular model of strategic communication, let's add an infinitesimal amount of information to the receiver. And we'll ask, do the payoffs and equilibria survive this small change? And there's a standard observation in the literature, which I only mentioned for comparison, and I'll mention it a few more times for comparison, which is that in the Bayesian persuasion model, the predictions are informationally robust. Can change the information a bit, doesn't change the conclusions very much.
Does that mean changing the prior of the receiver? Or is
Changing, no. So basically, the way we model it is we give the receiver some, and not also a signal, but just a very uninformative, very informative.
Okay, is it different than changing his?
It's different because it's like giving him a random prior. But the distribution is very close to the initial prior.
So the sender does not know it. That's
The sender knows the distribution, but doesn't know the realization.
That's the difference.
Yes.
Okay.
Basically, and so yeah, so you could always have, I said it's an extreme assumption that the sender has all the information, the receiver has no information. You could also have a model where the receiver has some information, but the sender knows this information and more. And then you could map that into this.
So then the question would be robustness with respect to changing the prior.
Right, so that would be different. So here we're saying we're giving the receiver a little bit of information that's not known by the sender.
Okay.
Okay, so the standard observation is that Bayesian persuasion is robust in the sense that I'll talk about, and the main paper is about cheap talk models, and we'll show that here the equilibrium may or may not be robust. So we characterize when they are robust, and when they're not robust, then we find out which payoffs and which equilibria are robust.
So there are three people here: the receiver, the sender, and someone is giving information that the sender does not know. The receiver.
Yeah, so that's the third party is nature. So that third party has no interest. It's just a signal that they get. So there are two players, but there's also nature generating randomness. And we focus on a particular setting, which people have studied a lot in the past few years, which is state-independent sender utilities, meaning the sender has a specific utilities for the different actions that the receiver takes, regardless of the state of nature. Like the politician always wants to be elected, doesn't matter if he's a good politician or not. And there's going to be a binary state space. And basically we have four results. First is we give necessary and sufficient conditions for these sender optimal payoffs to be informationally robust. And very kind of loosely, it's either that the equilibrium is trivial, meaning that the sender actually doesn't share any information with the receiver just takes a default action. Or the sender does share information, but fully reveals one of the states with positive probability. These are kind of simple-ish equilibria, and here they are robust. Our next result is about what happens when these equilibria are not robust, and we give a characterization of which actions are played in a robust equilibrium. And what do robust equilibria look like in this setting? Then we look at the payoffs that are robust, and we give some characterization results about what are the robust payoffs that the sender can achieve. Okay, so we have full characterization if we limit the space of receiver's private information, and we have some bounds for more general private information. Okay, so it's all about the model. Actually, we're looking for a good application, so if anybody has ideas, we're open to suggestions. So there's some related literature. The first bullet is, the first paper is one of the foundational papers in Cheap Talk. The paper by Nassim and Levid is more closely related to what we're doing. So I'll mention this, but their approach to how to analyze Cheap Talk games is what we're going to adopt as well. And they also give the characterization of the sender optimal equilibrium when the sender doesn't have any, has state independent preferences. One thing that distinguishes our paper is that we look at a setting where the receiver also gets private information. So, Chief Talk is huge literature. So there are also papers in Chief Talk that have looked at what happens when the receiver gets private information. The second bullet has some of these papers, basically looking at a Crawford-Sobel kind of setting, but where the receiver also gets private information. The paper is actually most closely related to ours is this Ishida and Shimizu paper. Their setting is more similar to ours, but they analyze a setting where the receiver has a lot of private information. And they basically show that if the receiver is almost as well informed as the sender, and sometimes there's no communication, even if their preferences are very close to each other. We're kind of looking at the opposite spectrum, what if the receiver has a tiny bit of it.
But you mentioned closeness of preferences.
Yeah, so in their setting, there's like a threshold above which you want one action, below which it's the other action, and how far they are. These papers here look at different aspects of different robustness notions for strategic communication. So, for example, this paper by Dillman, he looks at what happens if there's an infinitesimal cost to sending different kinds of messages in a Chief Talk model. What kinds of equilibria are robust to that? And Neil and Kuzmich look at what happens when there's some uncertainty about the sender's preferences. Okay, so kind of this robustness issue has been examined before, but different notions of robustness. And philosophically, the robustness issue of models is, I think, most closely related to this paper, this Paji Morris paper and subsequent work, where they look at equilibria and complete information games, but then they introduce some uncertainty about higher order beliefs, and they ask what equilibria are robust to this uncertainty from the modeler's point of view, from the researcher's point of view. Okay, so philosophically, we're doing the same thing. We have some model, and we're asking what happens if the researcher is a little bit uncertain about some of the specifics of the model. So if it's not uncertainty about higher order beliefs, it's uncertainty about information the receiver has.
Which paper that you know is that? Maybe not special.
Robustness to incomplete information, something like that.
So it's not about a specific concept of robustness. It's,
They have a specific concept of robustness.
Okay.
Perturbations of the higher order belief hierarchy.
Okay.
Yeah, and then say equilibrium is robust. For all small perturbations, still the equilibrium is arbitrarily close to the original one. Okay, here's the outline. There's a model and example, which I'll kind of present together, kind of skip back and forth. Some people like the model, some people like the example. Then I'll have some results, and then I'll have 2 more slides.
Go
ahead.
You have something like 200 slides here, right? Before
Yeah. They go with a lot of, steamer slides. All right, so modeling. Let's start with an example. Okay, we have 2 states of the world, omega, 0 and 1. The receiver is a policymaker who has to choose a policy. He chooses either the policy P0 or the policy P1 or no policy at all, called the P empty set policy. He prefers P0 in state 0, P1 in state 1. And in particular, let's say he prefers a particular policy, like P0, if there's at least a 60% chance that 0 is the correct state. And 60% chance that 1 is the correct state, he prefers policy 1. And if he's in this kind of between stage, then he just prefers not to implement any policy at all. Okay, that's the receiver, the policymaker. There's a sender, the expert, who knows the true state of the world. The sender has different preferences that are independent of the state. He doesn't care what the true state is. He gets different utilities depending on the policy chosen by the receiver. So policy P0, he gets utility 3, P1 gets utility 4, and least of all, he doesn't like no policy at all. He only gets utility 1. Okay, so kind of a typical representation of this kind of example is like this. This is called the indirect utility function. Basically, what we have here on the x-axis is the receiver's belief that the state is 1. So at the prior, it's pi, he's 50-50, he doesn't know what the right state is. And then for any other belief, it's not on the x-axis here. On the y-axis, we have the sender, the expert's utility, assuming that the receiver has a particular belief and takes the optimal action. So for example, if the receiver's belief is at 0.8, then the optimal policy is P1. And given that the receiver takes action P1, the sender gets utility 4. And if the belief is 0.2, then the optimal policy is P0. given that it takes action P0, the sender gets utility 3. And at the primary, we can see that the optimal policy for the receiver is the no policy option, in which case the receiver gets utility 1. Okay, so this is the indirect utility of the sender as a function of the receiver's belief. Okay.
Again, the sender utility doesn't depend on the state.
The sender's utility doesn't depend on the state, just on the action.
Why it's indirect?
It's called indirect utility because it's just it's indirect.
Ah, it's a
right? It's
function
a function of the
okay.
receiver's belief rather than of the action.
And again, it just sorry. So the receiver strategy is either to policy 1, policy 0, or
Or
none.
no policy at all.
Okay.
Okay.
So about
So if he's more than 60% certain about a given state, then he'll choose the appropriate policy. Here P1, here P0. And if he's kind of in this uncertain range, then he'll choose no policy.
This is be concrete. Suppose the sender wants the receiver to go to an Afghan to do the demonstration.
Yeah. So either I go
cares
to
about
pro,
either
I go to against.
cares about is whether it goes to demonstration.
Yeah.
He doesn't care. He doesn't give you utility from the belief.
Right.
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 And in this case, it's a Pareto up there. That's a Pareto superior, right? Everyone's better off. The 4 line makes everyone better off, right?
No, it depends on what the
How does
receiver
it
believes.
down there?
If the receiver believes that we're closer to state 0, then the receiver prefers this action. He prefers to go to the left of Venom. And if he believes that these guys are right, that this is the state, then he prefers to go to the right of Venom. And only if he's near uncertain, then he prefers to stay home.
And the sender is going to, okay.
And the sender wants the receiver to go to one of the Afghanot. He prefers the right one slightly over the left one, but he prefers both to no Afghanot.
is it the same as if the receiver has reaction?
Reactions, yeah.
Okay.
Yeah,
Nothing is it.
Nothing, yeah. Reactions. Instead of concrete example.
And the sender is the bagel salesman.
The what?
The one that sells bagel in the Afghanot.
Yeah. So his bagel stand is closer to where the right Afghanot is happening to the left, but the people from the left can also come.
I don't give you an example.
What?
With us being.
Okay, so why would the store owner know the state of the world? I don't know in this example.
He's also a taxi driver and they know the best.
Okay.
So what can the sender say to the receiver?
Right, so we'll get to that in a sec. So this is the example. Let me just formalize it in the model because some people prefer the model. So we have a binary state space, and that's our whole paper is just about binary state space. There's some common prior, pi, the probability of state is 1. In our example, it's 50-50. There's some finite set of actions. In our example, it's 3, but it could be any finite number. The receiver has a utility function that depends on the action that he takes and also on the true state of the world. Okay, so he has preferences over which action to take, depending on his belief. And actually, we can actually split the optimal actions into intervals. So if the belief is in this interval, then there's one optimal action. If it's in some other interval, then there's some other action that's optimal. And depending on what interval the belief falls in. And notice that here, but also in the example, one thing that I didn't point out is if the receiver is exactly at 0.4, he's actually indifferent between these two actions. Okay, which means he can also mix. Okay, he's indifferent. Okay, the sender we said has a state independent. What?
Is it crucial to the result?
Yeah, it's going to be important that he can mix.
Those intervals may come again. I mean, you can have 2 intervals for the same action.
No, you can't have two intervals in the same action.
Okay.
Yeah, I mean, there's single crossing.
Okay.
You have an example we should have?
If those beliefs could be anything.
No, the beliefs are binary, right? There's a belief the probability of the state being 1. So if here action A is optimal and here action A is optimal, then it must be also in the
Okay.
kind of floater of these two, right? Yeah, probability. Okay, there's a sender we said a state independent utility function. He just cares about the action. And we're going to make an assumption that there's no indifference. Like a genericity assumption. Okay, there are no two actions that he values exactly the same. You can say what happens if there are, it's not interesting. For our result. Okay, so and then what I presented before, this graph is the indirect utility of the center, which is a mapping from delta, which is the belief, receiver's belief, the probability of state is 1, to a utility function. Right, it's like the V of pi, it's all possible utilities for the sender given that the receiver plays the best reply. So in the interior of these intervals is just the unique best reply, and at these edge cases, actually it's the whole line because you can get any mixture of two actions. It's a whole vertical line.
The enemy takes one action, right? Throws a coin over.
You throw the coin and then takes one action. Yeah. Alright. Yeah.
Just what is your time?
I'm sorry.
Pi is the
Pi is the belief.
And can you show us again the pi?
Yeah.
Thanks.
So why feel five is something? Huh?
Pi is a subset of R because V of pi is the utility of the sender at belief pi, right? So for example, at belief 0.8, it's singleton, it's just 4. But at belief 0.6, it's the whole set from 1 to 4, it's the whole interval. Because the receiver could be mixing, he's indifferent between these are all optimal for him. So you can get all of those utilities. Right, so there's actually a line connecting here this to this and this to this. That's why it's a set. Okay, so let's go back to our example. Notice in our example, if we're just at the prior of a half, and the sender doesn't send any information, the receiver gets utility 1. It's the least utility that he gets in this example. And the question is, can communication increase the sender's utility? Can he do better if he does communicate? And of course, the answer is going to depend on what kind of communication he engages in. Okay, so just quickly, for comparison, let's talk about Bayesian persuasion. Okay, which is a strong form of communication, strong in the sense that the sender has strong ability to commit. Basically, what happens in Bayesian persuasion is the sender commits to a signaling scheme before he learns the state of the world. Okay, so the sender doesn't know the state of the world, he commits to a function that maps each to be realized state of the world into a distribution over messages, over signals. Okay, for example, say if the state turns out to be 0, then I'll send you this message. If it turns out to be 1, then I'll randomize between these two messages. Okay, and the receiver sees what the sender committed to, then the state is realized, and the sender sends the message according to this mechanism that he committed to. And here's just for comparison, here's the optimal Bayesian persuasion scheme in our example. Okay, in our example, the sender is going to commit to sending one of two messages, H0 and H1. And what he does is, first of all, if the state is H is 1, he'll always send the message H1. If the state is 0, then he'll mix. He'll send some message H0 with probability 2/3 and message H1 with probability 1/3. Okay, now what happens when the receiver gets a message from the sender? So if he gets the message H0, then he knows for sure that the state is 0. Right? Because the only time the sender sent this message is in state 0. Okay, so his belief is now at 0. Believes with probability 0, the state is 1. Probability 1, the state is 0. On the other hand, if the receiver gets the message H1, then either the state is 1 and we're up here, or the state is 0 and we got this point. So he does a Bayesian update. Okay, so figure out what's the probability that the state is 1 given that I got message 0, message H1.
No, it's
No?
okay. It's okay.
No. This yields the posterior belief 0 and 0.6. I'll show you a second clarification. Right? If I got the message H0, then the receiver's belief is 0. He knows for sure that the state is 0. And if you get the message H1, then what's the probability the state is 1? Turns out to be 0.6.
5.6.
Well, it's the problem.
1/5.
Yeah, it's a half over a half times 1 plus a half times 1/3. Right, it's space over. H0, sorry. Thank you. Okay, basically you generate the posterior 0 and posterior 0.6. Okay, and then with the basic result invasion, and then the utility of the sender when this happens is exactly, you look at this line connecting the 0 to the 0.6 at the prior pi. Up here, that's the utility that the sender gets
Under this scheme
under this.
is multiple equilibria, but this is one of them.
This is the unique sender optimal equilibrium.
So, man, I don't get this 0.6. I don't know why. 1/3 of H1 in 50%. 50%, 1/3 of.
It's a half divided by a half times a third. The half divided by a half plus a half times a third, or 1 divided by 1 1/3.
Which is
Which is,
3.
okay, yeah, so I think probably. You might be right, math might be wrong.
0.75.
Okay, so that's 0.75. Thank you. The point is that the optimal scheme generates at least 0.6 and 0. Okay, that's 0.6. The optimal beliefs are going to be 0.0 and 0.6. Has to be the point here where we're indifferent. And this dotted line that I do is called the concave closure of the indirect utility. It's basically the smallest concave function that's weakly larger than the indirect utility, weakly above the indirect utility function. And the main result in these Bayesian persuasion models is that the optimal sender utility is the concave envelope, of the indirect utility function. Okay, so this gives us the optimal sender utility for any prior. So look at any prior here, the optimal you can get is the value at this concave envelope. Okay, so that's in Bayesian persuasion. And but notice that here the fact that the sender committed to the mechanism is necessary, because the sender strictly prefers sending message H1 over H0. Because in H1 he'll get the utility 4, and H0 he'll get the utility 3. Okay, so if he hasn't committed, he'll always want to send H1. It's only the fact that he's committed, he's in this Bayesian persuasion model, that we can get this thing to work. Okay, so that's Bayesian persuasion. And what happens without commitment? Well, so now we talk about the cheap talk model. Okay, so the cheap talk model is similar. The sender also sends a message, or just to differentiate, let's call it a message M0 and M1. But here there's no commitment. Okay, the sender observes the state of the world and then sends some message after he observes the state of the world. Now, in order for there to be some equilibrium where the receiver believes something from he knows or understands the distribution from which this message came from, the sender actually has to be indifferent between sending both messages. But if he sends both messages in equilibrium, it can't be that he strictly prefers one message over the other, because then he'll always send that message. So there can't be an equilibrium where he sends both messages. In order for him to send two messages in equilibrium, he has to be indifferent between them.
We have two messages only because we have two actions. That's the result.
Two states, yeah.
Two states.
Because it's two states, two messages are sufficient. Yeah, that's the result. That's the standard result. So the result of the Klasky repeat says if you look at this game with cheap talk rather than Bayesian persuasion, then the optimal payoff the sender can get is not the concave closure, but the quasi-concave closure. What's a quasi-concave envelope? Sorry. What's a quasi-concave envelope? It's the same as the concave envelope, except instead of looking at the smallest concave function that's above the indirect utility, you look at the smallest quasi-concave function, which is basically a function that just has horizontal lines. Okay, look at the smallest function that's just made of horizontal lines that are weakly above the indirect utility function. And in this example, it's not the dotted line, it's the dashed line. Okay, this is what you can get with cheap talk. So in particular, in our example with cheap talk, you look at pi, the optimal value is 3. It's lower than what you can get with Bayesian persuasion, but it is better than what you can get without any communication. So cheap talk buys you something here, just not as much.
How do you do it?
How do you get 3? Okay, how can you get utility 3 with cheap
But
talk?
this is a general result of them?
Yeah, this is a general result. You can get the
What are the
quasi-concave.
conditions?
What?
What are the conditions?
The conditions for this result are state independent preferences of the sender. That's it. Okay, how can you get this utility of 3? Right? Why is it the quasi-concave equilibrium? So it's helpful for our paper also to look at how you can get this utility. So I'll describe the equilibrium. So in state 1, the sender always sends the message M1, okay, like in the Bayesian persuasion setting. In state 0, again he'll mix, and I guess the probabilities are wrong again, but the way
No,
he
it's
mixes.
correct. It was correct. You just have to switch between 1/3 and 2/3.
Oh, okay.
So it was written there. He said you something about mistake. The mistake was in the first place.
Okay, but here it's correct. Okay. So it's the same probabilities as in this example. Again, you generate the same beliefs, 0 and 0.6. Okay. Notice that on receiving message M1, the belief is exactly 0.6, which is where the receiver is actually indifferent. In Bayesian persuasion, we assume that it takes the higher action. With cheat talk, we're going to assume that when he gets this message, he's going to mix. And in fact, he's going to mix because he's indifferent, he can mix. And he's going to mix in such a way that the sender's utility is exactly equal to 3. Okay, this is easy to see in the picture. At this belief, at belief 0, the optimal action for the receiver is what leads to utility 3. There's no mixing here. But at the belief 0.6, we're going to make the receiver mix. Okay, he's indifferent, so he can mix, and he's going to mix in such a way that the sender's utility is also 3. So note that the sender is now indifferent between sending the two messages. Okay, and so this is an equilibrium. Okay, the receiver always takes an optimal action or distribution over actions given his belief. The sender is indifferent between the two messages, so he's willing to play along with this equilibrium, and this gets the sender utility 3 in equilibrium. But cheap, no commitment necessary.
So that's one equilibrium, it's the best for the sender. How many
Yes.
equilibria are there?
Yeah, take any 2 points. I mean, there's equilibria that yield utility 1. You can also have equilibria that yield anything between 1 and 3. Okay, you can generate beliefs 0.4 and 0.6 and create beliefs that are, here and here. And so any payoff between 1 and 3 works. You can't get anything above 3.
In this equilibrium, does the sender have to know the receiver's belief? Yeah.
The sender has to know the
He doesn't
receiver.
care
Yeah.
about the belief, he only cares about the action.
Yes, right. But he cares about the belief, but that generates the action.
He imputes the belief from the action.
The other way around. He generates the belief, and then he gets the utility from that belief. Right? Because his mixing over messages is what generates the receiver's belief. So he generates the receiver's belief.
Okay, so it's endogenous to his.
Yeah. So each one has to be optimal relative to the other one.
So the receiver, I'm missing something. The receiver utility.
Mhm.
Do we know it?
The receiver's utility here.
Because the mixing depends on.
Well, I didn't say what the receiver's utility
So it
function is.
depends
I
on-
just said what his optimal action is in each interval.
Right.
Yeah.
So to support this equilibrium, we
Yeah.
should know the probabilities.
No.
Depends on his utility, no?
No.
When,
No. This belief. I don't care what his utility is. I care what this is his
yeah,
optimal
when
action.
his belief is,
When it
or
is- I also don't care what his utility is, but I do know that at this belief, the utility he gets from this action and from that action are the same. And they're higher than the utility he gets from that action.
Okay.
I don't care what the utility is, I just care about what his optimal action is. Okay, so this is in the example, but it's a general result. So even in a quite a general setting, I think you could have a continuous state space, continuous action space. You get the optimal sender equilibrium with cheap talk is the quasi-concave envelope. Okay, just one thing that we'll notice for later is that for this to be an equilibrium, the sender has to be indifferent between the two messages. Now, it doesn't matter what the realized state is, right? Because the state doesn't affect his utility. He's state independent. Okay, so that's kind of the key thing making this an equilibrium that wasn't present in the Bayesian persuasion setting. The additional thing you need when you have G talk.
If he's indifferent, why send a message?
He's indifferent between these two messages. The messages still provide information to the receiver. The receiver does act differently. The sender is indifferent between this and this, but the receiver is not. Okay, so this is an equilibrium. Okay, so that's the model that we're going to adopt. But we're looking at a setting where the receiver now obtains some additional information that wasn't present, that the sender doesn't have, or the sender has, but he doesn't know exactly what that information is. And for the example, let's suppose that the receiver obtains a signal. Just for the example, it's a binary signal. The signal is either S0 or S1, and it's equal to the state with probability Q.
So now this is your addition.
This is our addition.
Up to now.
Up to now, it was first Bayesian persuasion, then the Tarski revision. Now, this is our change. Now, we're going to give the receiver an additional signal. Now, think about Q. This is the accuracy of the signal. If it's exactly equal to a half, then it's completely uninformative. So let's make it a little bit bigger than that. Eventually, you want to look at what happens when it approaches that. Okay, it's a binary. In this example, it's a symmetric signal, and it gets the right value, S0 in state 0, with some probability Q bigger than that. So you might get the wrong signal. And the question is, how does this affect the sender's equilibrium utility? Is it still close to a third? Or is it going to change? So first, kind of a note, under Bayesian persuasion, the information, this additional information to the receiver can only be harmful to the sender, because the thing that the sender committed to is already optimal. And so if you perturb it a little bit, you can only decrease the utility. But again, in standard observation, if you look at Q approaching a half, then the harm approaches 0. Basically, the sender can get almost the same as he could even without this receiver private information. This doesn't change the prediction.
Just with the Bayesian persuasion, the sender knows exactly the state of the world.
In both cases, the sender knows exactly the state of the world.
But the sender does not know the signal that the receiver receives.
Right, just a distribution number.
The distribution given the state.
Yeah. Exactly.
Okay, so why doesn't it change much?
Well, think about the Q approaching a half. Right, it's going to change the receiver's prior from half to a half plus epsilon or half minus epsilon. Right, depending on how small Q is.
The sender just
Well, he doesn't want to ignore it. He wants to take it into account a little bit, compensate for it a little bit. If he ignores, then he's splitting it in half. He doesn't want to do it once. Right? So,
What if he ignores it? Does he lose more than epsilon if the
yeah, if he ignores it, he loses more than epsilon, because in order to get this to work, you needed and we put in Bayesian persuasion, okay, we put at exactly 0.6, he played this action of 4. But now if you give him even an uninformative signal, very uninformative signal, then if he gets a lower one, then now he's down, this one gives unique optimal action, he's not going to play 4. With probability close to a half, he's going to play the action that gives the sender 0. And he doesn't want that. So what he's going to do is he's going to take this, instead of making him the belief at 0.6, he'll make it at 0.6 plus epsilon. So that on either realization, he's still above this cutoff 0.6. That's what a little bit is.
It shows that the sender has property that is
Close to the same.
that will be now in the Bayesian persuasion there is no question of
There's no,
it's only an optimization problem.
yes, yeah,
It's not a question.
no.
Fine.
this robustness of this Bayesian persuasion, does it depend on having finitely many actions?
No. So again, the robustness is with private information of the receiver that's somehow close to being uninformative. But obviously, if the receiver has a lot of private information, then different things could happen. And the question is robust a small addition of private information. And here, Bayesian persuasion is pretty robust. What about cheap-like? So before talking about robustness, I want to understand what does an equilibrium with cheap-like look like now that we have additional private information. And what you'll see is actually the conditions for there being an equilibrium are now stricter than without private information. As opposed to Bayesian persuasion, where it's still just an optimization problem. So I'm going to give you a strategy profile for the sender and the receiver, and then I'll explain why it's an equilibrium, and I'm trying to understand what has to be true for this to actually be an equilibrium. So again, in state 1, the sender always sends message M1 like before. In state 0, the sender is again going to mix, but now he's going to mix differently than he did before. Right? So what happened before is he's going to mix in such a way that on the high message M1, the receiver was exactly indifferent. He was at 0.6. But now remember, the receiver is also getting an additional signal, which could be either S0 and like pushing the belief down, or S1 pushing the belief up. And so here, the sender is going to mix in a way that on this message and the lower signal of the receiver, the belief is exactly 0.6. Okay, he's not going to put the belief exactly at the indifference, but he's going to shift it over so that on the low signal, that's where the indifference is. Okay, so it's going to look like this. Again, there's going to be posterior 0, and now there's going to be posterior 0.6 plus something, so that on the low realization, that's the left kind of arc, that's exactly where the receiver is going to be indifferent. Okay, so that's the strategy for the sender. The strategy for the receiver is, again, when he's indifferent, he's going to mix. But now he's not going to mix so that the utility of the sender is 3. He's going to mix differently. He's going to mix so that the utility of the sender on the expected utility on belief 0.6 is x. Why x? What's x? X is such that it has to satisfy something. It has to be the case that the sender utility, the expected utility of the sender, given state 0 and message M1 is equal to 3. Okay, so again, let's look at it in the picture. He's gonna mix in such a way that at belief 0.6, the utility is actually lower than 3. Why is it lower than 3? Because when the sender sends this message, what's his expected utility? Well, given state 1, state 0. In state 0, he has to look at the probability of getting the message S0 and then the mixture, plus the probability of getting the message S1 and utility 4. And this expected utility has to equal 3. So that means this x has to be lower than 3 because on the high signal, the utility is higher than 3. Okay, it has to balance out. And so that's this equality here. The expected utility of the sender in state 0, given message M1.
Yeah, but let's say that you change the model a little bit. Say that the signal that the receiver, the independent signal, not the
Conditionally independent signal, yeah.
that one is continuing.
Yeah, so we're gonna have that as well. That's the result.
Then like might not get
No, we do. That's the result in the paper. You can always find somewhere to put the belief so that there's going to be an equilibrium. It'll be indifferent. Okay, so let's just so that's what an equilibrium looks like. And notice the two things have to be true. Okay, first of all, it has to be true that in state 0, right, in state 0, the sender is mixing between two messages, which means he has to be indifferent between these two messages. But given state 0, he has to be indifferent. In state 1, in our example, always sends the high message. So he doesn't have to be indifferent, he has to weakly prefer the message that he's supposed to send in state 1. Okay, because he's not mixing. But if we had a different equilibrium, or he mixes in both states, then he would have to be indifferent between both messages, conditional on this state and conditional on that state. Okay, but either way, there are two incentive constraints that have to hold for the sender. For each state, he has to be either indifferent between the messages or weakly prefer one message over the other. Okay, and this is actually the main difference between what happens under private information of the receiver and what happens in the original setting. There was one constraint, right? You have to be indifferent between two messages, and the states didn't matter. Here, the states matter. Okay, here's the model of this. So we said that the receiver gets some private information. In our example, it was this binary signal. But more generally, we're going to say that he gets private information from some information structure, where S is some measurable space that could be continuous. And then there's a distribution over S in state 0 and a distribution over S in state 1. Okay, so for each signal that he gets, he can do a Bayesian update and figure out the likelihood of the different states.
The receiver knows this full information, right? The receiver knows that the sender has a preferred outcome.
He knows the sender's utility, and he knows the preferred outcomes, and he knows also, and the sender knows the distribution over the receiver's extra signal. Common knowledge of everything.
The receiver knows that the sender is not going to act strategically in some way to improve the chances of the receiver's preferred outcome.
Well, in equilibrium, you can't, right? In equilibrium, the equilibrium is such that the sender is going to be indifferent between everything that is supposed to. It doesn't have any way to improve, otherwise it's not in equilibrium.
That's how that's work.
Mhm.
So the receiver doesn't actually, the sender doesn't actually know what's going on, right? Because, is that right? Because the receiver is mixing strategy.
Yeah. He has no way though to get the sender to not mix, right? That's the receiver's optimal strategy.
It's interesting. My intuition would say that,
Okay.
I don't know if the sender would be interested. The third position would somehow that the receiver job.
Well, he is, right? So even in our example,
Mixing.
the receiver is mixing, but that still helps the sender. Right? In our example, without any information, the sender was getting this default action of 1. And here we can push it up to 3. Right? It still does better than you could without communications.
That's expected values.
Yeah, the expected values. The realization could be 0, could also be 4. Okay, the expected values.
Can you repeat on the point you mentioned that here,
Mhm.
the sender on one state should be weakly preferred one message and the other indifferent with the rest.
Yeah.
Right? This is the idea?
Yeah, this is in this
It
example.
must be,
In this example, because in this example, in state 1, the sender only sends one message. He's not mixing.
always ever.
In this example, in state 1, he always sends message M1, and so he doesn't have to be indifferent. He just weakly prefer the message that he
Right.
sends. But in state 0, the one that generates kind of this interior belief, there he has to be indifferent.
That's interesting, that's generating uncertainty for the receiver. So really, the receiver is mixing. In a sense, it's not really uncertainty, but it means.
Yeah, there is uncertainty because the receiver is also not sure what the true state is. He only has a belief about it. So there is uncertainty.
It's affecting the uncertainty and causing mix.
Yeah.
It's not sure anymore, I mean, well, you're not sure about what it speaks.
Well, no, he gets to believe 0.6. He was 0.5, and now he's more sure than he was before. Right? It has that. The belief has moved closer to certainty, but still very far.
All of this information sharing should increase the receiver utility. If you put
The
some numbers.
receiver's utility? No.
Yeah, if you put some numbers.
No.
So
Not
it
at all.
might be that he prefers not to hear even the sender. The sender can decrease by giving information his utility, no.
Can he decrease by giving him information?
It's not, doesn't make sense. This is a characterization of functionality, right, of decision making. More information is better, so if you put numbers, it's only,
Yeah, he
it can
can't
only
increase,
increase it.
he can only weakly increase.
Right, it's not misinformation,
On this information.
but it's another model that you use.
So it's like. Because it always. Okay.
This is the formal model of this information structure the receiver receives. Technical thing, which is going to be important later, but I'll repeat it later. Basically, the signal S, we call it S0 and S1. We could just give S the name, which is the posterior belief that it induces. So in our example, it won't be S0 and S1, it'll be 0.6. Those are just the names of the signals.
Isn't it without the signal?
Yeah, so it's a belief given posterior, given in prior one. So if you start with prior half and you got the signal, what would be the induced posterior? So it's not 0 and in 6 it's 0 and something else. So in our example, the signals are S0 and S1. The distribution is in state 0, you get a message S0 with probability Q and S1 with probability 1. When it's Q in state 1, it's the other way around. And with this identification, S0 is 1 minus Q and S1 is Q. Because if you started at belief 1/2, getting S0 would, or getting S1 would shift your belief to the Q, and getting S0 would shift it down to 1 minus Q. Okay, what does an equilibrium look like? So first of all, our sender strategy is some function from the state into a distribution over messages. That's the sender strategy. The receiver strategy is a function from the message that he receives, the signal that he receives, into a distribution over actions. And a pair of strategies is an equilibrium if the following two things hold. It's basically what I said in the example, but this is the formal version of it. First of all, the receiver's action is supported on this expression. Basically, I'm just going to say it in words. Given the message and the state and the signal that I received, what are the possible optimal actions given the belief that these induced in me? Okay, and I can play any distribution over these potentially optimal actions. Okay, that has to be the receiver strategy. You have beliefs, there's some optimal actions, maybe there's a unique optimal action, maybe there's a distribution over actions. I have to play some distribution over these actions. Okay, that's the receiver. For the sender, the following has to be true. For any state and any message that he sends, okay, if he's supposed to send this message with positive probability in this state, if I have to send message M0 in a particular state, then it has to be that I weakly prefer, okay, this is the distribution over, this is the expected utility. Expected utility, given the receiver's actions in this state, has to be higher than my expected utility if I deviate to some other message. Okay, this is for any other message that's ever sent with positive probability.
So you can originally.
It's not only any.
Well, if M prime is never sent with positive probability, so we're going to assume this, otherwise we're going to have some messages that are off equilibrium. So we're just going to assume that, and then you have some other belief that those messages. This inequality has to hold only to messages that are sent with positive probability, but relative to other in this state, but relative to other messages that are ever sent with positive probability.
Then
Incentive constraint.
Yes. The sender cannot be true.
Yeah.
But then it's different.
Right.
But the different message can be anything.
Yeah, so here to say anything any M prime doesn't have, so
Yeah. On his side.
what?
The M prime shouldn't, what you said seems wrong. For every M prime, why should M prime be sent with positive probability? For any M prime.
So you can add here for every M prime, and then add that if there's some message received that's not in the support of the equilibrium strategy, then the receiver's belief is such that it induces the worst possible payout to the sender.
So
Okay, it's not M prime that is not sent with positive probability
in any state?
in any state.
state.
It's not well defined, right? You can't condition on this message. Because it's supposed to happen with 0 probability. So you can't condition on this message. Right? So I can't write this expression. The question is what happens if he does send a message that's not in the support? So let's just have some worst case for the sender. Okay, we're gonna look at worst case over distributions anyway. So let's look at if a message is sent that's not in the support, the belief of the receiver is going to be such that his optimal action is the worst possible for the sender. Okay?
No, that's something not in the support this receiver does not have any belief about the state of work, not formally, not consistent. Receiver cannot form belief, you cannot say what is going to be the actions.
So the belief of the receiver is part of the.
Yeah, so that's what I'm saying. So let's define the belief in a way that's the worst case in the center.
No, is it?
Sequential equilibrium is there's some belief, okay, but there's some law about it. So think about in a perfect Bayesian equilibrium is one where you specify the belief without any conditions. Here, eventually, we're going to look at an infimum over information structure. So let's just look at the infimum over the beliefs, kind of the worst case belief for the set. Okay, that's going to be consistent with what's going to have to be next.
So you define it this way, but
Yeah, so I define it.
you couldn't define the equal concept, I don't know, differently. So
You could have the belief here as some off equilibrium action, something else. Yes.
yes, so that's not, I don't know, the only conceivable definition of equilibrium, but this isn't about the sequential equilibrium. That's not the point here.
No.
Okay.
But this is a constraint that maybe does not define it. You have better.
So what I'm saying is there is a way to complete this definition, so there's an equilibrium, right? So it makes it a complete definition.
In order to complete this, you have to say what is the receiver's
Off equilibrium beliefs.
reaction to
Yeah.
to
Yeah.
to offer equilibrium.
Right.
I don't get this.
Not beliefs, it is not even beliefs.
So off equilibrium messages.
Offer equilibrium messages, so there is no belief.
There's no belief. There's some, what are you doing out? Well, in these notions, in perturbation equilibrium, sequential equilibrium, you specify a belief at off equilibrium messages.
If you just
Yeah, then it's just order is actions at an off equilibrium message. So if you want, you can have it as a worst case action, or you can have it the default action, like what he does at the prior. Any of those will work.
What does mean is conceptually? You see, if I understood correctly, you have invented an equilibrium concept. Why should we invent?
First of all, you need to decide the standard. It's a standard notion of an equilibrium. This is a standard equilibrium. Yeah, it's
You
specified
just
for
can only
communication.
specify the equilibrium, specify what.
It's
What the user does in off equilibrium message.
Okay,
So
okay.
what Ronen said, in order to make it in the equilibrium, it says that the receiver does the worst action for the sender.
Yes,
or the default, or its default action. That also works.
but does he have to do that? Is that the only way to define a Nash equilibrium? That's my question.
No. This is- No, every Nash equilibrium has to satisfy one and two. And everything that satisfies one and two can be completed in condition.
Completed, what does it mean completed?
Of equilibrium, you can say what the third do such that this is it.
I see.
Okay, let's just see how this constraint shows up in our example. Okay, in our example, in state one, only the high message is sent with positive probability. Right, so the only n for which this has to hold is message one. Okay, so given state one, so looking at the F1 distribution, given state one, I only need message one to be preferred to the other message, M0. Now in state 0, the sender mixes between the two messages, which means that in state 0, this has to hold and the converse. Right, so here actually it needs to hold with an equality, because he's indifferent between the two. Okay, this is in state 0, under the distribution, conditional on distribution of the signal, conditional on state 0. Okay, and this is the main difference between setting with private information and without private information. Without private information, we already said the sender needs to be indifferent between the two messages in both states, but this message leads to a utility that's independent of the state. Okay, so it's just this one indifference in the state. With private information, again, the sender needs to be indifferent between the messages, but here, the state does matter to the utility. Because depending on what the state is, the receiver gets a different distribution over signals, which affects the receiver's actions, and so the sender's payoff. Okay, so here the equilibrium requires two incentive constraints from the sender, one for each state. And those incentive constraints could be inequalities or they could be equalities. Okay, so let's go back to our example. So we showed in our example that here's an equilibrium. And again, this equilibrium is an equilibrium because in state 0, the sender is indifferent between sending message M0 and getting utility 3, and sending this message, which in expectation gives him utility 3. This expectation is given state 0. Right? It's with probability Q, you're indifferent and he gets this X, and with probability 1 minus Q, he gets the high message and he plays the action and gives him utility 4. Notice that actually in this example, having private information on the receiver is beneficial to the sender. Why is it beneficial? Well, we said that in state 0, the utility of the sender is exactly 3. But in state 1, the utility has to be strictly higher than 3. Right? Because in state 1, he gets a high signal with higher probability, and the lower signal with lower probability. So if when it's in state 0, the utility was exactly equal to 3, in state 1, it has to be strictly higher than 3.
Yeah, but what is the probability?
Well,
In state 1,
that's
it's
almost
always
it.
always.
Yeah, it's always. Okay, which means that and again, we said this doesn't violate the incentive constraint because in state 1, he didn't have to be indifferent. You just have to be you have to weakly prefer message 1. Here, actually strictly prefers message 1. Okay, so the seller's unconditional utility is strictly higher than 3. Okay, it's 3 in state 0, but higher than 3 in state 1. But like with Bayesian persuasion, if you look at Q that approaches a half, right? If you just have an infinitesimally informative signal of the receiver, then the sender's utility does converge to 3, which is the same as what happens without private information. Okay, so in this case,
Because in state 1,
yeah,
the
Sender always send M1.
sender,
Always sends M1.
he always sends M1.
Yeah.
In state 0,
So
he
you
makes
see,
this.
state 1, the sender,
sends M1.
okay,
And there is a small probability that you will receive more than
state
Wait.
1, the curve of the sender is going to be something like the line on the line connecting the two
No.
black
it should be in the
holes.
black hole, in the black point.
No, the black point gets utility 4. He's going to get
Something between
Right.
he gets something between 4 and 3.
Yeah.
Yeah.
But as the Q goes to 0,
Yeah, this dot is going to go down to 2. Because as Q goes, think about what happens at Q equals a half. What happens at Q equals a half? Right, where it gets, or really close to a half. Right, it has to be that on the left signal, message M1 in the left signal is indifferent with 3.
in state 0,
Yeah,
the expected curve of the sender
Yeah.
is going to be 3.
Always.
yeah,
Is this correct?
yeah.
Okay. And in state 1,
Mhm.
it's going to be strictly above.
Yeah, it's strictly above.
Above 3, something
Yes.
between 3 and 4.
No, it's not, yeah, it's very close.
No. It's something constant.
No. Because think about how is it possible that in state 0, the sender is indifferent between sending the messages? Okay, it has to be that when he sends message M1, his utility is 3. How does that happen? Well, he gets payoff of X with probability Q and payoff 4 with probability 1 minus Q. And that has to equal 3, right? As Q approaches a half, this X has to approach 2. Right.
But this only happens in state 0.
Yeah, in state 0. But this X, right, is independent of the state. Right? So because he's indifferent in state 0, we know that this payoff approaches 2. Right? And in state 0, he gets Q times X plus 1 minus Q times 4, which equals 3. In state 1, he gets 1 minus Q times X plus Q times 4. But because Q.
In state 1, the little arrow always jumps to right.
No. It jumps right with probability Q and left with probability 1 minus Q. And Q approaches a half.
Okay,
It can all, yeah, if it's uninformative, then right, these jumps are right, these are jumps in the beliefs. Because right, if it always jumped to the right, then we would jump to here. And because these are small jumps, these are jumps in the beliefs. So you have to jump to the right with some probability and to the left with some probability. And it approaches 50-50. And actually these lines get closer together, these jumps.
okay, so these jumps are small and also the probability between the close.
Approaches a half, yeah. As Q gets closer to half.
Again, the equilibrium we're talking about is the center optimal. There are infinitely many other equilibria.
Yeah, you can generate other equilibria if you want to.
And just to be sure, the probability Q changes, but not the size of the jump.
No, the size of the jump.
The accuracy is Q.
The accuracy is Q, but as Q gets closer to a half, the jump is smaller, right? Because the jump is the change in the posterior belief of the of the receiver. And if Q gets closer to a half, the change is smaller because the message is less and less informative.
I think you could have played it, no?
What do you mean?
You could have generate a signal that you can control over Q and the size.
Yeah, we'll do that too. This is just for an example. But you're right. Okay, so in this example, it said that the private information is beneficial to the speaker, but go right here. As Q grows less informative, it converges to 3. Okay, in this example. And one of our results in the paper is that this holds for actually any vanishing information structure. I mean, any information structure that grows to or approaches non-informativeness, not just binary information, just any information structure. And in this case, we say that the payoff of 3 is informationally robust. I'll give you a formal definition. Okay, so here's the formal definition. Under information structure F and prior pi, let's call the maximal equilibrium utility of the sender VF star at pi. Okay, so this is with respect to a particular information structure F. Now let's face it's the best the sender can get, given that the prior belief is pi, and that the receiver's information comes from information structure F. Maximal sender equilibrium utility.
What we call optimal sender?
The optimal, yeah, optimal sender. So optimal sender, I call that for when there's no information. So I'm saying the best the sender can do, call it optimal if you want, given that the receiver has information structure F. Okay, now let's look at some small delta. And let's look at all information structures where the support is contained in a half minus delta, half plus delta. And the support of the information structure, these are the shifts in the beliefs, starting with a prior of a half. Okay, so all information structures that shift the belief by at most delta, call that F delta, the class of these distributions. So our question is, what's the maximal guaranteed utility for the sender under a cheap-cup equilibrium subject to infinitesimal private information? But that's what we're calling informationally robust equilibrium. So here's the formal definition. Define the informationally robust equilibrium utility as follows. We call it V hat of pi. So we're going to look at the best the sender can get under information structure F. We're going to look at the infimum over all F in a particular class F delta. So all the worst distribution over all distributions that don't change much. And we're going to look at the limit as delta goes to 0. Okay, so V prime, if it's equal to 3, like it is in the example, that means that for any information structure where the distribution is small enough, the sender can guarantee a utility of 3 for any information structure. Okay, so that's V hat. Let's look at the optimal value with an uninformative F. So this is with this is in the Lefnowski Levit paper. We'll call that V0 of pi, V0 star. And our question is, when does V hat equal V0? Right, like in our example, they're both equal to 3. I showed you with a particular information structure, but our result is that this actually holds for any information structure. And so here it is, these are equal. The question is, does equality always hold, or can there be a discontinuity at the limit? Remember, we're looking at delta approaching 0, but at 0, it's equal to v star, 0. Okay, so that's basically our question. Okay, and if there is a discontinuity, I'm also interested in what is the v hat? What's the best at the center you guarantee? That was the model in the example.
The limit can be something else. The hat can be something.
Yeah.
In the example, it's
So you tell me when to stop, so I have some results. I can look at the results. 5 minutes. I'll show you one result. Here's one result. Let's remember our actions are such that there's intervals where there's some optimal action for the receiver. And our first theorem says that we have equality if and only if one of the following holds. Either V0 is equal to V of pi. V of pi is the indirect utility. Okay, meaning that it's a trivial equilibrium. There's no message by the sender. If without a message you can get the optimal under cheaper, then yeah, so also with this informationally robust setting, you can get that. And so that's one case. Or if the optimal utility without private information is equal to the utility at the actions on either endpoint of the interval. So, right, so we have these intervals of where actions are optimal. There's some action that's optimal in state 0 and some action that's optimal in state 1. And then there are other actions that might be optimal if there's uncertainty about the state. Okay, so we're saying that the payoff is informationally robust if the optimal payoff is equal to one of these endpoint actions. Like in our example, right, the optimal utility under cheetah was equal to 3, which is the optimal utility in state 0. Okay, so here it holds. Okay, it also says something about the optimal center equilibrium. It means that there's always an equilibrium where the sender fully reveals one of the states with some probability. And in our example, he does. He reveals, right? There's some probability that he reveals that his state is actually 0. Okay, so let me just show you an example where it doesn't hold. And then I'll end the talk. So let's look at the same as the previous example, but we'll add a third potential policy for the receiver, which he prefers if his belief that state is 0 is at least 0.8. This is the worst for the center. Okay, our indirect utility function looks like this. The only thing I changed is I added this other action here. That's better for the receiver and if he's quite certain the state is 0. This is the worst action from the center. Okay, so here, this is the Bayesian persuasion which you can get. It's a little bit lower than in the previous example. But with cheap talk, the quasi-concave envelope is exactly the same. It's still 3. But you still get a utility of 3 in equilibrium with cheap talk, with no private information of the receiver. Okay, but here, notice that the utility of 3, first of all, you can't get it with no information. With no information, you get utility 1. And it's also not equal to one of these endpoints, that are 0 and 4. Which means that the utility of 3, according to the theorem, is not informationally robust. You can't get this payoff of 3, even with arbitrarily small private information on the receiver. And that's an implication of theorem 1. Okay, none of the conditions hold, so theorem 1 says not informationally robust.
So what you can get? Something.
Actually, the information robust payoff here is 1. You can get 1. It's the best you can do here.
Just I want to see in the picture. So why can't you do the same treatment before?
Yes, I'll show you why I can't. I have pictures. Okay, so the only way to do it, first of all, is to have you can't have a belief that's at 0 or 1. You can't induce beliefs at the endpoints, right? Because then the utility has to be equal to the beliefs at the endpoints because of the indifference. So you have to induce interior beliefs. So you need 2 equality conditions to hold, 2 incentive constraints holding at equality. Why can't you do that in this example? Well, one thing you could try is you can have the beliefs maybe in the interior of an interval and here is the endpoint. Now this doesn't work. Why doesn't this work? Because on this message, the utility is always 3. And on this message, the utility is either 4 with probability Q and this with probability 1 minus Q in one state, or 4 with probability 1 minus Q and this with probability Q in the other state. And both have to be equal to 3, which is obviously not possible. Because something like this isn't going to work. You could try something that you have this also kind of at a mixing going on. So first of all, this you can't do because here on the left, on the low signal, you get something lower here than here, and on the right signal, you get something lower here than here. So again, you can't have equality, right? These need to be equal. So you might want to try something like this. Now, what would have to be true for this to be in equilibrium? Well, let's look at a particular state. Let's look at state 1, for example. So you get, say, the high message with probability Q and the low with 1 minus Q. Okay, so for this to be in equilibrium, you need Q times 3 plus 1 minus Q times this to equal Q times 4 plus 1 minus Q times this. That's in state 1. You also need 1 minus Q times this times Q times this to equal 1 minus Q times 4 plus 1 Q times this, right? You need this to hold under 2 different distributions of the left and right realization. And if these are different values, which they are in our example, because we have this assumption about different payoff utilities, you have 2 different weighted averages that have to give the same number, but you can't. That's impossible. That's the intuition for why it doesn't work. Right, so there's a lemma. It says
So
exactly.
the equilibrium is the worst compared with the case with no equation.
Yeah.
It's 1 here, and then
Actually, here the only thing you can guarantee is 1.
what is the result of Robid here?
You get 3. It's a
The,
concave closure.
what is the quasi-concave in this picture?
3. It's a straight line to here, then straight line from here to here, then the top line.
Ah, it's like stairs,
It's like stairs, exactly.
so you can skip over some.
You can skip over the 1. You go
Okay.
straight across on the 3.
Every time you
Yeah.
can
Yeah, always go
skip
up.
over lines.
Yeah.
And you have to share some information in 2 points, so you can generate. Okay.
Yeah, for Labid it's the same. It generates again these 2 points averaging to 3, and maybe this point, but any point in here actually, it doesn't matter. For him, it doesn't have to be an end.
With the perturbation, it's.
Then you can't do it anymore. Then you need 2 in center. Okay, so other stuff we have, what can you get? So actually here we can get 3, you can get 1, which is kind of different kind of equilibrium construction, and then proving that this always works.
So I could get only 1, and if I made the left line even smaller and smaller, so we have almost always 3,
This?
and just the endpoint is 1.
Yeah, you wouldn't be able to get it. It's still you can only get 1.
So that's another discontinuity of the model.
Yeah. Okay, so let me skip to the last 2 slides.
On this coefficient, I did like option.
Okay. So here's the result that I did show you. With necessary and sufficient conditions for the sender optimal payoff with no private information to be informationally robust, which is this either trivial or supported at an endpoint. Some other results that I didn't show you, we actually have a full characterization of what equilibrium that's robust does look like, and it's a characterization of what are the optimal sender payoffs. And this actually the way to get it is a reduction to some zero-sum game, which is kind of nice to get to that.